Go ahead, Mr. Proactor.
Thank you. I hereby open this academic ceremony in which Mr. Aditya Aradhye will defend his academic thesis, Strategic Communication and Manipulation. May I invite you to present a summary of your study and the conclusions of your thesis.
Dear Pro-Rector, dear members of Corona, dear family, friends and audience, in the coming 15 minutes, I will shortly present the summary of my PhD thesis titled Strategic Communication and Manipulation. My PhD thesis, the research is based mainly on the broad two topics, game theory and social choice theory. In game theory is the study of strategic interaction between players with personal motives. In games, there are a number of players. Each players take different decisions. We also call these decisions as actions. These decisions together determine the outcome of the game. Each player receives some kind of reward, we call the payoff or utility, corresponding to this outcome. So the main objective in these games is to study the behavior of players, how the players play, what strategies they use, and to analyze solution concepts like Nash equilibrium, perfect equilibrium. We also study the utility of the players and the exact occurrence of the different outcomes. The second broad topic is social choice theory. Social choice theory is the study of collective decision making. In these settings, there are a number of agents. Each agent has preference over different outcomes. So as an example, each agent can be considered as a voter, and different outcomes or different candidates that they can vote for. So the decision maker sees all the preferences of the agents and he chooses an outcome depending on those reported preferences. So the main objective in this setting is to design and analyze decision-making rules in which agents do not have an incentive to misreport their true preferences. My research is divided into 3 chapters, and these 3 chapters are divided into 2 parts: the strategic communication and strategic manipulation. Strategic communication is part of game theory, and I will talk about sender-receiver stopping games and sender-receiver stopping games with multiple senders. So in this settings of studying strategic communication, there are a number of players, and these players can have either complete information about the game, or they might be partially informed about some aspects, some parameters of the game. And so the main feature of these games is how the information is being transmitted from informed players to partially informed players. So sender-receiver stopping games we extended into the second chapter when we consider the same game with multiple senders. So the second part is strategic manipulation. It's a part of social choice theory, and we study multi-dimensional binary domains. In these domains, as opposed to the classical models, we have multi-dimensional domains. So the main thing is to see how does the voting structure change when you have multi-dimensional domains. Now I will talk about each chapter in detail. I will start with an example and then I will come to the details and the results. So sender-receiver stopping games. Let's consider a scenario where there is a fully informed, there's a financial expert and there is an investor. So the investor on the right has a stock which he decides either he wants to sell or hold. So the investor wants to sell the stock whenever he can obtain the large sum of money. So if he thinks that by selling the stock today, he will earn a lot of money, he will sell it, otherwise hold it for tomorrow. So today he will not get any money, but he will have an option to sell it tomorrow or at some point in the future where he expects to get more money. However, this investor cannot observe or does not fully understand the market. In the sense, he has partial information about the market. Hence, he approaches the financial expert on the left. So this expert can observe the model well and understands the market well, and hence can make informed decisions to the investor. However, this expert has its own personal motives, let's say in the form of commissions. So given this fact, investor knows that the suggestions given by the expert to the investor are based on the expert's personal motives. So the suggestion that expert gives to the investor, so investor thinks if he should obey his suggestion or not obey. So this is a setting of we model as a sender receiver stopping games. So sender is the expert in our case and receiver is the investor. And we study the repeated interaction where at each period they interact, the expert sends the information, the investor either decides to sell or hold. And as soon as he does not sell this stock, the game continues. So what are the goals? So we wanted to design a model which captures the features of sender receiver games and stopping games, which are very standard in literature. We wanted to study the information transmission from the sender to the receiver. We wanted to characterize perfect Bayesian equilibrium in the game. Perfect Bayesian equilibrium is one of the standard solution concepts used in game theory. And we wanted to analyze this equilibrium in finite horizon and infinite horizon, whether they can play for finitely many periods or infinitely many periods, and discounted or undiscounted payoff functions. Which means if in the case of discounted payoff functions, payoff tomorrow is discounted via some factor, which can be looked at as, for example, inflation. So our results are as follows. We show that under some conditions on the discount factor, there exists a unique perfect Bayesian equilibrium. And if these conditions are not met, there is no perfect Bayesian equilibrium. In this equilibrium, the sender plays threshold strategy and the receiver completely obeys the messages which are sent by the sender. So in the unique equilibrium we have, our receiver completely obeys the sender. So sender has exactly what he suggested. And hence, in this equilibrium, sender obtains the best possible payoff that is possible in the game. Next, we talk about our second model, which is sender receiver stopping games with multiple senders. In the one sender model, because there was only one sender, receiver under equilibrium had to obey the sender, and he had no source of other information. So hence the natural extension to the previous model was to consider what if there are multiple senders. In this case, the investor has more access to the more information, and maybe if that he might be able to exploit this information so that not only one sender cannot exploit the lack of information of the investor. So the goals, as I said, for the sender receiver stopping games with multiple senders, to study the perfect Bayesian equilibrium. We also wanted to study if the receiver is able to exploit the information which is obtained from multiple senders, if he can obtain a better payoff because he has access to the more information, and also to study the externality effect of an additional sender to the payoffs of sender and the receiver. So if you introduce one additional sender, does that affect the payoffs of sender and the receiver in a positive way or in the negative way? Our results are as follows. We show an existence of a perfect Bayesian equilibrium that extends the unique perfect Bayesian equilibrium that we found in the first model. Unfortunately, in this model, there is no uniqueness of equilibria, and it's also impossible to characterize all the perfect Bayesian equilibria, but we still show an existence of nice perfect Bayesian equilibrium. This perfect Bayesian equilibrium is center collision proof, which means even if a group of centers come together and they try to manipulate together, they do not get better payoff, so they do not have any incentive to form a coalition. As another result, we also construct an example of game which shows that having an additional center can still result in lesser payoff for the receiver. So it's not necessary that just because you have additional centers, hence the additional information, receiver is better off. This is not always true. And hence this example serves as a counterexample for that. Then we come to the third chapter, which is multidimensional binary domain. As an example, consider a scenario where in Parliament, Parliament members have to vote on whether they want to approve or not approve a number of different bills. So there are the number of bills, and each Parliament member has a preference on each bill, whether they want it to be approved or not. So while voting for each bill, they either say yes or no, whether they want it to be approved or not. So the decision maker, let's say in this case, head of the committee, the decision makers takes all the preferences and then creates a final outcome, which is basically final decision on each bill, which whether it is passed, whether it is approved or not. So we model this problem scenario as a social choice problem in which the agents are different members of the parliament, and the different alternatives are the different components are the different bills which need to be approved or not. In this kind of problems, one of the main important things we want from the social choice rules we design is strategy proofness, which means no agent would want to misreport their true preferences in order to achieve a better outcome. We also study a bit stronger notion called group strategy proofness, where a group of agents together misreport so that each member of the coalition get at least better outcome. So we consider two different notions of strong group strategy proofness, weak and strong group strategy proofness. So the goals was to analyze component-wise majority rules, which are very standard in these domains. So component-wise majority rule means you look at every component and whether if you have high number of yes votes or high number of no votes, you just approve that particular component depending on that without taking other components into account. We wanted to study strategy proof rules, and we also wanted to study weak and strong group strategy proof rules. So the results, we show that component-wise majority rules are strategy proof, but they are not weak group strategy proofs, and hence extension, they are not strong group strategy proof. We construct examples of strategy proof rules and also weak group strategy proof rules. And with minor assumption on number of agents and components, we show an impossibility result for strong group strategy proof rules. So it turns out that in this setting, strong group strategy proof rules are strong group strategy proofness is very strong notion, but others are weak. To conclude, in this thesis, we studied 3 different settings. 2 of them are in sender receiver games and 1 in social choice theory. But in the first 2 chapters, we characterize and analyze the perfect Bayesian equilibria in this game. And in the 3rd chapter, we partially, not completely, but we partially characterize strategy proof and group strategy proof rules in the multidimensional binary domain. Thank you. Thank you for your attention. I give now the word back to the prorector.
Thank you, and thank you for a nice presentation. The opposition will be opened by Professor Stan van Hussel of Maastricht University. And Stan van Hussel, you need to unmute, then we can hear you better.
I will always say boomer, but that's not a point. Dear candidate, let me start by saying that I read your thesis with pleasure, realizing that your technical abilities are higher than mine. But it was very nice to see your wonderful results. I have a kind of a lame question, actually two lame questions. And I know that many members of the jury think that all my questions are lame, but for today they're right, but I hope not always. The first question, I'm going to take you to the extremes of your thesis, by the way. And the first question is therefore about the acknowledgement. You mentioned a lot of people. I never knew that our department was so big. But one stood out, and that is that you spoke highly of the cooking of Farzaneh. And what I would like to ask you is, what do you think of the cooking of Dries or Nilofar or me? And of course of your own. Maybe you should answer this question first. Go ahead.
Dear highly esteemed opponent, thank you for the refreshing, bit easier question to start with.
Okay. So, are you sure?
Well, it's subjective, of course. I was flatmate with the Farzaneh for more than 6 months, and then we were stuck during the COVID, and then we had to eat each other's food. So I had to compliment. It was not by choice, but it was kind of compulsory. With Dries, I did not expect, considering the knowledge of Dutch food, but Dries, the food that Dries cooked a couple of times for us was incredibly well. And also, Stan, your food was amazing. Although when you cooked, half of the work, more than half of the work were done by others. So, and Nilufar's food was pleasantly surprised with that. It was very nice.
Anyway, your onion bhaji is also fabulous. So let's move on to the next question. And that's, as I said, the other extreme, where you talk about the impact of your thesis. You claim that on the one hand, you would like to have an accurate model of the problem that you are facing. And on the other hand, you have to simplify it simply because otherwise models become too complicated. The example of a real life example of a sender-receiver game is that you talk about competing firms exchanging information. I never knew that competing firms would exchange information at all, so please explain that a little bit. But what I'm more interested in can you specify, concretize a little bit on how this example actually can be seen as a sender-receiver game? And maybe why you simplify. Sorry?
Dear highly esteemed opponent, thank you so much for your question. So firstly about competing firms sharing the information. So I said that in a bit broader concept, not exactly related to my topic, but it's more about information transmission in partially informed players. So in that case, in case of the multiple firms, there can be a firm which has all the knowledge, and in the other cases, there are multiple other firms with partial information, and they might benefit from combining the forces against the bigger firm. So this example was to serve as an example of generic partial information transmission, not specifically to my model. So to coming back to your second question, so can you please repeat your second question?
How is the model is a simplified version of reality? Where is, in this particular example, are features simplified, left out of the model? which type of features should I think of?
Yeah. So in the simplification that we make is in the model we assume the state of the world, which is the uncertain parameter of our model, is drawn uniformly and identically from past periods, which is not necessarily true in the real world. The real world is much more complicated, and the uncertain parameter is not coming it from uniform or fixed distribution. It's it's a specialized case.
Yeah, I understand. Thank you very much.
Thank you.
Thank you. And I believe we need to sell the literature on information exchange and oligopolies a little more. That would be my problem. Now the opposition goes from the chairman of the assessment committee to member of the assessment committee, Professor Ehud Leder of Tel Aviv University.
Thank you. Hi, Aditya. First, congratulations for the nice dissertation. And I would like to refer to the sender-receiver chapters. You assumed fully informed sender or senders, receiver who is completely ignorant, two signals, increasing functions with respect to the state. And each one of these items could be generalized. I would like to ask you first, what kind of extensions you think would, with high probability say, or likely to result in new mathematical or behavioral outcomes?
Dear highly esteemed opponent, thank you so much for an interesting question. If I say the generality, the extensions you suggested is about two actions, monotonicity of functions, and I think there was a couple more which I missed, I think.
Let me ask a specific one. There is a parallel literature on social learning where agents are partially informed about the real state of nature. Here, all the senders are fully informed.
Yeah.
What would you think be the case in which the receiver, the senders are partially informed? They get some noisy information about the real one. And then what happens if the receiver is not a complete ignorant, but he knows a bit, he gets some partial information about the real one? Would it have a similar or results that would be in some sense analogous to cascades or whatever?
Yeah, thank you so much for clarification. So I think this is a very interesting direction where sender does not have full information, but partial information, and the receiver has a bit more information. Without choosing the specifics, I cannot answer exactly, but I think as long as the sender is completely informed about what about the receiver's information, many of the results, again, this is just on the hunch, I will need to work on this further, but I believe as long as the sender has all the information that the receiver has, some of these results might continue to hold. And if the receiver has even more information, then it's very, very unclear. But again, I will need to, it will depend a lot on what kind of information or what kind of uncertainty sender and receiver has. So I will need to dig deeper, but it's a very interesting question, and then I will definitely make a note of it for the future research. Thank you so much.
Thank you.
Thank you. And the opposition will be continued by member of the assessment committee, Professor Jérôme Renaud of Toulouse School of Economics.
Hello. Let me first congratulate you for the nice thesis. I think it's very well written. And the scope also is quite large with different topics. And I've appreciated a lot this model of sender-receiver stopping games. Okay. I would like to ask a question about chapter 2 and 3, but mostly chapter 3 when you have multiple senders. So here the messages are binary, either continue or quit, or they're interpreted as continue or quit. But we may think of richer languages, like they could send any number between 0 and 1 maybe. Do you think this could enlarge a set of equilibrium payoff, of PBE payoffs, or could this maybe sometimes improve the welfare of all players at equilibrium if we allow the senders to send richer messages?
Dear highly esteemed opponents, thank you so much for your interesting question and kind words. This question we thought a lot, particularly when we were thinking about the first chapter with one sender, one receiver. So I will answer the question in that model first, and then I'll come back to the setting with multiple senders and one receiver. In one sender, one receiver case, having multiple messages definitely increases the number of different equilibria, in the sense that because having large, richer strategy space, you have more equilibria. But if you consider the outcome of the game, in the sense that when the game is stopped, that or the expected payoffs of the sender and receiver, this is not changed, in the sense that the only expected payoffs in the case of one sender, with the case of two actions and multiple actions, does not matter that much, because sender has the best possible equilibrium he has, and he can always pull all of this message in the same. In the multiple sender case, however, things are a bit different, because there are many different equilibria apart from the regular strategy equilibrium that we considered. So there is no uniqueness. And unfortunately, there is a lot of equilibria in which the main feature is about how can different senders correlate with each other's strategies. So I believe this will still increase the space. This can increase the space of strategy, the equilibrium, because having access to more than two actions, the group of senders are able to do much more than before. So I definitely believe that there's much more equilibria when you have more than two actions. I hope I answered your question.
Thank you.
Thank you.
And the opposition will be continued by a member of the assessment committee and associate professor here at Maastricht University, Tom Storken.
Dear candidate Aditya, I also want to congratulate you with your work. It was really nice to read. You were very accurate in writing down and very efficient. So I really could grasp your thoughts in a very short way. So I liked it, the way you presented it. My special attention, given my background, goes of course to chapter 4 on collective decisions on multiple binary domains. There you study some rules which satisfy automatically unanimity, anonymity, neutrality, and various conditions of strategy proofness. So what I especially liked from this chapter was the positive results you have there, because in social choice we have numerous negative results, and we should, I think, strive for positive results. I liked in particular the positive result of proposition 412. So although you might not agree with it, but having also rules which are not component-wise or dimension-wise, it is nice to have these. So much for the good, I would say. So now let me come to some criticism. I also missed some things, and that could be because of my age. I'm already growing gray, so I'm getting a little bit of choosy. And so what I missed is, a mentioning of May, his work from 1952, in which he does essentially your one-dimensional case. And that would have been nice if you had this in, but anyway, it does not. The results are nice. On the other hand, you propose a model, and what I also do, at least I try to do when I work on models, I try to analyze how sensitive the model is with respect to the choices you made, so on the parameters. And for this, I would like to, at this moment, I would like to go to your definition of neutrality and see how sensitive your model is with respect to your specific choice on neutrality. So neutrality in general is something like, okay, if I rename the alternatives, and renaming means, of course, a permutation like you do, then this translates in the outcome. So this translates in the preferences, and this translates in the outcome. Now, in general, if you would have an unrestricted domain, then you would not have any problems by taking any permutation. But you have here a restricted domain, something like a single peaked preference. So you have a peak, and that the further you diverge from this peak in some measure, and that is the Hamming measure, the L1 norm, I would say, the lower your preferences. And now neutrality, you cannot just take any permutation, because this could destroy the single peakness. And what you did is you took a permutation which renames the dimensions, so to speak. So one component is put on the other, and vice versa, or several of these. Essentially, if you go geometrically, what you need is, of course, a permutation which does not alter the distances. And so you could take, what you do is a hyperplane which is on a 45-degree line, and this maps your hypercube again onto your hypercube, plus it leaves the distances unchanged. But you could also have taken additional hyperplanes which are on which map a 0 onto a 1, so which are parallel to all the non-involved, so that the things that really not change, not change, I would not say, but they are parallel to the axis which you do not permute, and which maps 0 onto 1 or for one axis. So you take the perpendicular bisector of one one pair of alternatives which are close to each other. Now, this also does not change the distance, and therefore maps a preference what you are studying on a preference what you are studying. Essentially, you would say, okay, if I take such a mapping, I say that whether I choose 0 or 1 for one component, that doesn't matter. I map these onto each other. And I guess if you extend this neutrality to also allow for these permutations, you get a more demanding neutrality condition. And that's true, of course. And one of the two questions which I actually are going to pose is the following. So if you extend, so you strengthen this neutrality with this extra type of permutations, then this might alter your model. And my question is, how much will it alter? And as we have only a small time, I would suggest that you dwell on the result of lemma 4.7 on page 107 and proposition 4.9. So in 4.7, you say that you have a switching point, huh? And in lemma 4.9, you study component-wise rules which are strategy proof. Does this still hold also under this extra condition? Actually, do these rules satisfy this neutrality condition? On the other hand, to really go for sensitivity, you can also say, okay, let's not use neutrality at all. So if we look at rules which are only unanimous and anonymous and have some strategy proofness condition, and then my question would be, does the result of theorem 4.25 on page 121 still holds? So there you show that there is no rule. Yeah, there is no rule which is strongly group strategy proof, given that there is a number of agents and there are at least 3 components. So if I drop neutrality there, can you still have this result? So that are my 2 questions. Is it clear?
Yeah, but dear esteemed opponent, thank you so much. Yeah, I think questions are clear to me. So first of all, before I start answering the questions about the single pickedness, our model is not exactly single picket according to the classical definition.
Yeah, I'm aware of that. Single pickedness is you have a peak in your hypercube, and then if you go away, then certainly it's not the single pickedness with respect to linear orders or something like that. I am aware of that.
Linear, yeah, exactly. Okay, I just wanted to clear my understanding. Yeah. So the alternate definition of neutrality is definitely very interesting, where instead of switching rearranging the component or renaming the component, you rename what is 0 and 1. So you replace 0 and 1. We consider this model, we were thinking of this model, and we are not first to think about this model, in fact. And in this model, actually, as far as I remember, there has been work by people in Amsterdam, particularly Ule Andres and Serene Burton, I think, or Zoe. I don't exactly remember who were the co-authors, but so they have considered this model, and they have, so the model, if you consider neutrality with respect to 0 and 1, the model becomes much simpler. And in fact, they show some impossibility result, or I don't exactly remember, some kind of characterization result which is stronger than ours. So they consider group strategy proofness, but they also even consider the stronger notion of group strategy proofness, in which, if I believe correctly, it was something like it's a group strategy proof where the group had some size limit. So can only 3 of 4 players can form a coalition, and so that result was stronger than us, and the proof was not really particularly challenging. So introducing 0 to 1 neutrality without assuming our notion of neutrality makes things much easier, and which has been done before. And as far as answering what happens to our results when you introduce neutrality, if I think about lemma 4.7, which talks about switching point, I believe that because you switch, because you assume that 0, 1 are equivalent to each other. I believe that the switching point, if the switching point would be somewhere in the middle. If n is a1, the switching point will be n by half of n. And I believe lemma would still continue to hold, although I need to check everything.
Yeah, my guess is that you are back in the framework of OK May.
Okay,
So you get only strict majorities will hold.
Yeah, so in the characterization,
the switching point only holds if you have an odd number of agents.
Okay, yeah, and in that case, yeah, I think you're right. And then the majority is the only rule that survives the group.
Yeah, absolute majority is the only rule that survives.
Yeah. And
so
to talk about
the rules of 4.9, are they neutral with respect to this extended neutrality?
So we are talking about component-wise majority rules. Yes, they are, because you
only if you have absolute majority. Yeah. Again, you have the same problem. Otherwise, they don't exist.
Because component-wise majority only considers the number of zeros and ones. And if you replace each 0 by 1, and in case of odd number of agents, if you simply replace 0 and 1, then for each agent, the component-wise majority will still continue to hold.
Yeah, sure.
Yeah.
But they don't exist for even number of agents.
Yeah, for even number of, it depends on the tie-breaking rule, which makes matter very complicated.
You don't have a tie-breaking rule there.
There, okay.
I'm sorry. But a more interesting question is the last one. If you drop neutrality, do you still have your negative result of 4.25?
Our proof certainly does not work because the way we construct the counterexample does not, so that does not work for neutrality. And if we drop neutrality, we do not have the proof for sure. But if I have to guess if the results still work, it's a bit difficult to say, because if you drop the neutrality, the space of social choice, the space of rules is much higher and much more complicated. So for me, it's a bit difficult to answer this question.
Yeah, okay, I understand.
On the risk of sounding completely wrong.
Yeah, okay, I understand. Thank you for your answer.
Thank you so much.
Maybe you need a weaker intuition for that somehow. The opposition will be continued by a member of the assessment committee and assistant professor here at Maastricht University, Anna Sheleva.
Yeah. Dear candidates, dear Aditya, I have met you at many locations on several continents. At the very beginning of your PhD in Maastricht, in Paris, New York, Finland, at conferences, and Tel Aviv on your research visit. These places have different climates and cultures, but one thing that remained constant is you endlessly talking about research, whether it's research topics or a career in research. And more than a year ago, when due to the pandemic, the atmosphere wasn't, there are less jobs around, it's hard to move abroad, and this is especially true in theory. It's not surprising to me that you, someone who's so very passionate about research, still received a postdoc right after his PhD. So first of all, congratulations on that. And I assume that you're very glad about today, because right now the topic of discussion is not only research in general, but your research specifically. So let me ask you about that. I will talk about chapter 2 and 3. You mentioned there are models with a finite and an infinite time horizon. I would be interested in how do you compare these models to each other? So how are they related? Why is it mentioned in infinite time horizon? Why is it mentioned in chapter 2 and not in 3? And your thesis has some new parts compared to a year ago. So for example, in the impact of the thesis you mentioned on page 139, we want these settings to depict the real life scenario as accurately as possible. And a few pages before on your summary, page 136, you say, so the game never stops and both players receive payoff 0. So when I think about reality and then I read this, I mean, I think you understand my questions. I would be interested, how do these relate? How do you see these relationships, both in terms of models and also to reality?
Dear esteemed opponent, thank you so much for your kind words and for your interesting questions. So the first question about how to relate finite and infinite horizon. So first I will talk about chapter 2, one sender, one receiver model. Here we actually have very nice relation between finite and infinite horizon. The proof works very differently because for finite horizon we have backward computation, and for infinite horizon we don't have that. But in this, the relation is very nice in the sense that if you consider the strategy under equilibrium, particularly the threshold strategy of the sender, and if you consider the threshold values in finite horizon at any horizon t, and as you grow, let t grow and let t to converge to infinity, the threshold values converge to the threshold values which are threshold values of sender's equilibrium in the infinite horizon. So in some sense, we have a small result somewhere that as you let t grow, the equilibrium in the finite horizon converges to the equilibrium in the infinite horizon. So in that sense, we had very nice result, and I was very happy when I found that when we found that result. As to answer why infinite horizon is not explored in chapter 3. Chapter 3 with multiple senders, the setting becomes much more complicated with the presence of multiple senders. And as I said, there is no uniqueness of equilibrium. But I was very interested to know if I could extend that result from the chapter 2 to chapter 3, saying, consider the regular strategy of equilibrium, which we have clearly defined in the case of multiple senders. I wanted to show that the regular strategy equilibrium in the finite horizon, as you let t converge to infinity, stays equilibrium in the infinite horizon game. To show that result, I would need to show some kind of convergence of threshold values. But the thing is, because of the interaction with multiple senders, computing or finding any result about threshold values of each sender becomes way more complicated, because all the threshold values of different senders are intertwined with each other. Hence, that result turned out to be much more difficult than I expected. I still believe that that might hold, but unfortunately, I do not have a proof for that. So if I could find a proof, I will be very happy at some point. The second question about the impact. Yes, so of course, there are both true to real life versus theoretical beauty. And of course, when I define models, I would want to be as accurate to reality as possible. But still, in deep down, I'm a theory person. So as long as something is theoretically aesthetic, I would definitely interested in pursuing that. Unfortunately, the result you mentioned does not make sense in the real life, but at least it's theoretically beautiful. So I'm still interested in that and would definitely want to keep as a part of my research.
Thank you for your answer. And since we have limited time, we'll discuss it after the defense. What do you even mean by infinite time? So irrespective of the results, it's a question whether, if you want to talk about reality, whether talking about infinite time makes sense. Let's talk about it at a different time.
Thank you.
Sorry. Thank you. And the opposition will be continued by Professor Arunava Sen of the Indian Statistical Institute in Delhi, India.
So, hi Aditya. Let me congratulate you on a very fine thesis. I believe I played a small part in the early part of your career, and it gives me great pride and pleasure to see what you've achieved. So, turning to questions, let me again focus on chapter 4, your multidimensional binary model. It seems to me that your model is also closely related to the model of Barbera, Sonnenschein, and Zoe in Econometrica 1990, which is also a model with unit cubes and so on, but where you do not have the preference structure where you can weight components differently. It's also, I think, related to the models on Rn, not on the cube, but on Rn, and there with Euclidean preferences. And for instance, there is, there is a thesis written in French by Gilbert Lafon in 1980, which may not be accessible, but he wrote a paper later with, which I can send you the reference later. Bord and Le Breton and this thing, and you can do a lot of geometry on that. And I was just, my comment is to, that if you haven't seen this, this literature, there are a couple of them, papers, I would say, with Euclidean preferences on Rn and so on, that you might get, be an interesting reference point for your results, and perhaps might give you some ideas of some sharper characterizations and so on. Yeah, that's all I had to say. My first question in. Thanks.
Dear highly esteemed opponent, thank you so much for your kind words and for your interesting question. Indeed, the chapter 4, the project with Hans, was indeed inspired by the discussions that we had in Delhi all the way back in 2015 with you and with Swaprabha. And that was for the first time I was introduced to social choice theory, and which made me very interested to work in that. Thank you so much for all the references. I would definitely contact you afterwards. When I was discussing with Hans about several times, he also mentioned the geometric interpretation related to cube, and I don't remember if we talked about Rn particularly, but we talked about cube, and we even were considering to write a section in a paper and in the thesis about the geometric interpretation of the model and see how the other models correspond to that. And it's definitely very interesting thing that we wanted to do, but just due to the time constraints, we didn't manage to do that. But indeed, it's very interesting, and it's very nice to see the geometric structure and try to see how the results, what do they say on a cube. So it's definitely very interesting, and in the follow-up work, I would definitely take up that suggestion. Thank you so much.
Thank you.
Thank you. And the opposition will be continued by assistant professor here at Maastricht University, Bas Dietzenbacher.
Dear candidate, also on my behalf, I want to congratulate you with your achievement, the completion of your thesis. I think it is well written, well structured, and I learned a lot from it. My question goes again back to chapter 2, maybe also to chapter 3. You restrict attention to responsive strategies for the receiver to avoid bubbling strategies, which are, as you write, fairly uninteresting from a game theoretic perspective. Maybe you can explain first to the audience what is a bubbling strategy and why is it uninteresting from a game theoretic perspective? Is it interesting from maybe another perspective? But my question is more about the relation with your perfect Bayesian equilibrium that in your regular strategy profile, where the sender plays a sincere strategy and the receiver an obedient strategy, about the likelihood of this type of strategies to occur in reality. So can you think of situations where maybe a bubbling strategy is still played? Or is there a situation where it's, in your view, much more likely that your regular strategy profile is actually occurring? Or can we think of situations that both strategies are actually not so likely to appear, and maybe there are some other strategies that you can think of?
Dear esteemed opponent, thank you so much for your question and for your nice words. To explain to the audience what is babbling strategy is, babbling strategy is a strategy where sender sends some messages to the receiver, and the receiver plays some actions which do not depend on the messages at all. In some sense, he completely ignores whatever sender has to say and basically plays his own actions irrespective of what the message is sent by the sender. Why this is not interesting in game theory? Because in game theory, we talk about strategic interaction, in the sense that, or in this specific topic, we wanted to talk about strategic communication, how the information is passed from the sender to the receiver. Hence, because we wanted to talk about information transmission, in the babbling strategy, zero information is transmitted because, in the babbling strategy, when receiver plays babbling strategy, is the best response for the sender to not send any information at all. Hence, that's in this case, no information is transmitted. And of course, there's receiver does not make any use of the information. Hence, it is not interesting for game theoretic sense. About reality, if you consider the example of the financial expert and the investor, I think babbling strategy in that case would mean that an investor will hire financial advisor, pay the fees for his advice, and irrespective of what he says, plays about whatever he wants. So in some sense, he's hiring the investor and not making the use of him at all, which of course, there might be some crazy investor which does that, but if investor is smart, he should not do that.
So does that mean that playing a babbling strategy, in your opinion, is always stupid?
In our model, or in the setting which we consider, yes, which, I mean, unless they have some different agendas, sure, but if the objective is to maximize your expected payoff, then it's definitely better not to babble at all, not to babble. But if they have some different goals, which we did not consider in our topic, then it might, in a different setting, babbling strategy might be useful.
Okay, thank you very much.
Thank you so much.
You and the opposition will be continued by and possibly concluded by Professor Jérôme Renaud of Toulouse School of Economics.
Okay, I am honored to have the opportunity to ask a second question. It will be quick. In chapter 2, there is one assumption which is, I believe, quite important. With the payoffs of both the sender or the receiver are monotonic in the state. So they have very positively correlated utilities. Can you think of situations where they are not monotonic in the state? So maybe one is decreasing in some range, and still where the regular strategy profile will still be a PBE. Do you think this can exist, or you think as soon as you leave this world of completely positive correlation, this cannot happen?
Dear highly esteemed opponent, thank you so much for your interesting question. So if the payoffs are not monotonous or correlated, it's not necessary that regular strategy profile is not PBE. There are instances that there are examples where the payoff functions are not strictly increasing, but still it is an equilibrium, but it's only up to a certain extent. So for example, if you consider the other extreme case where sender's payoff is strictly increasing, receiver's payoff is strictly decreasing, this is the complete extreme case in the other direction. In that case, it's definitely true that the regular strategy profile is not PBE. So it really depends on the structure of payoff function and where the non-monotonicity lies between the 0 to 1 interval. So we definitely have examples where payoffs are not co-aligned and there does not exist PBE, but it's not always true. We can definitely find some examples where the non-monotonicity might not influence. It might be insignificant part of the interval, or maybe it just does not affect. So it's not necessarily true.
Thank you.
Thank you.
Thank you. Mr. Aradhye, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and of your defense. I request that you and your company await the results of our deliberations and our return.
Thank you.
Mr. Aradhye, the degree committee here present online has assessed the quality of your thesis and of your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Vermeulen is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
Dear Adi, dear almost doctor, I first have to ask you a question. Do you promise to work in accordance with the principles of scientific integrity at all times? To be careful and honest, transparent, independent, and responsible?
Yes, I do.
Good. By the authority vested in us by law and in conformity with the decision of the committee here present online, I hereby confer upon you, Aditya Aradhye, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, you will soon receive the degree certificate signed by the rector, the secretary, and the supervisor, affixed with the official seal of the university, as is now shown by the beadle.
Thank you so much.
Congratulations, Adi.
Thank you so much.
So the laudatio will be done by Matthias and Janos. So they will take over.
All right. So, dear Aditya, a long and intensive journey finally gone to its end. It's very good, and I suppose, so Dr. Aradhye, my congratulations to your PhD, to your doctoral thesis. And you can really say this is yours, and you can be really proud of yourself. I think you produced an enormously well-drafted PhD thesis. This has been already mentioned several times today, also by your assessors, by your peers, by your colleagues. So congratulations, and I'm very happy that I was part of this long journey. Your thesis consists of essentially 3 chapters on different aspects of game theory and social choice. In your first paper, you already start with a very high aim. You define essentially a new class of strategic interactions where you combine sender-receiver games with stopping games. And you analyze these classes of games with very high accuracy, efficiency, and it was remarkable how creative you were in finding your way through the proofs and the analysis of these new games. It was really a pleasure to see you grow over the years, and also for me, as maybe not an expert on stopping games nor on sender-receiver games, it was also very educative. I really learned something from your analysis and gained some more insights. So it was really a pleasure to talk to you, to work together with you, and in particular also to see you grow and get confidence into your own capabilities, into your own knowledge and your own skills. But not only scientifically, you're a highly esteemed colleague, right? Your PhD colleagues always spoke in very high tones about you. You made a lot of good friends, I think, now in your time here in Maastricht. So I guess your trip to Europe was enjoyable, I hope, and it's continuing. It's remarkable that you already started your first postdoc position in the Czech Republic. Given all these complicated environments we're working on in the moment, this is a high achievement, and I wish you all the best for your future. I'm sure we stay in contact, and good luck.
Yes. So dear Aditya, let me also congratulate you on writing an excellent thesis, which contains so many interesting and valuable results, and on receiving the very well-deserved PhD title. I will pick up the story of your PhD at the second paper, which is about sender-receiver stopping games with multiple senders. This paper is strongly related to the first one, but now there are multiple senders, which leads to different and new strategic complications. The topic is challenging, and I still remember the time that we had to think very hard to crack some problems. You managed to construct some natural and interesting type of perfect Bayesian equilibrium for these games And you showed, somewhat surprisingly to me, that it's not always beneficial for the receiver that he gets information from multiple senders and not only from one of them, as you mentioned at the beginning of your talk. We are planning to finish this paper very soon, and I'm looking forward to delve into the details very soon. I also know that you are passionate about social choice theory. You have a joint paper with Hans Peters on this topic, Group Strategy Proof in Multidimensional Binary Domains. This is the third paper of your PhD thesis. During your PhD, you spent 3 months in Tel Aviv with a group of Ehud Lehrer and Eilon Solan. It was an excellent opportunity for you to collaborate with such an excellent and friendly research group abroad. During your visit, you started a joint work with Ehud entitled Monotonicity of Values in Zero-Sum Repeated Games Imperfect Monitoring. We would like to thank Ehud and Eilon and the entire group in Tel Aviv for hosting Aditya so well. Aditya, I very much enjoyed our discussions, quite often about difficult and complicated technical issues in our papers, and your intrinsic passion for research. You are a very clever and versatile researcher with background in math and in computer science as well, and you have the quality to easily get interested in new topics. You are also a social person who makes friends easily, and you are still having many friends in Maastricht. I enjoyed spending social time together and playing card and board games and going to the movie theater. As for your career, currently you are a postdoc at the Department of Computer Science of Artificial Intelligence Center at the Czech Technical University in Prague. And you are working on with your colleagues on partially observable stochastic shortest path games and Stackelberg equilibrium. We, Dries, Matthias, and myself, wish you all the best with your future goals and dreams. With your excellent qualities, we are sure that you will succeed. Finally, we would like to thank the assessment committee and all the members of the opposition, in particular Ehud, Jerome, and Arunava for joining us from abroad. Aditya, congratulations again. We, Dries, Matthias, and myself, your supervisors, wish you, your family, your friends, colleagues a great day, and we stay in touch.
Thank you so much, Janos, and thank you so much, Matthias and Dries.
Dear Dr. Aditya Aradhye, also on behalf of the Board of Deans, I congratulate you with the honor that you have acquired. I hereby declare this ceremony to be ended.
Thank you.